Dear student, welcome to the video lectures on machine design part 1. This is lecture number 22 and the topic is design of riveted joints. Now, in the last few lectures you were taught how to design one non-permanent joint. Non-permanent in the sense that the joints are such that anytime they could be dismantled or disassembled if the requirement arises. So, these are the non-permanent type joints. There is another kind of joint which is known as the permanent fasteners or permanent joints. So, let us come to the types of permanent fasteners. Again, the permanent fasteners are those fasteners where the components can be disassembled only by damaging those components. So, here these are permanent joints. Now, again the components are held by two methods. They may be held by mechanical force, that is we give a large mechanical force such that they are held together. There are two examples. One is the riveted joint, which will be the subject matter of today's lecture. The second is the press fitted or interference fitted joint. This is again will be taught in somewhat details later afterwards, but here the purpose of the joint is that we press one part into the other and make a joint a permanent joint. The components could be held together by molecular force. There may be few situations, that is we talk of welded joints, we may talk of the soldered joints, and we talk of glued joints or using the adhesives. So, these are very important joints and will be discussed later on. So, now we start discussing on the riveted joints. Now, let us come to the basic geometry and the types of rivets. We must know what is a riveted joint, how does a rivet look like, and so on. So, let us see. A rivet, it looks like the following. So, this is the rivet. Now, this part which looks rounded is known as the head, and this part which is roughly cylindrical in shape, this is known as the shank, and this one which is tapered, it is known as tail. Now, this kind of rivet is made by forging. There may be hot forging or cold forging, which you know already. Now, how a joint is made with the help of this rivet? Let us look at the joint. What we have here, let us say we want to join two pieces together. So, this is a part and this is another plate. Now, we want to join them together. What do? We first drill a hole or sometimes punch a hole. If the plate is very thin, then we should drill a hole, and also of course, if the plate is too thick, then we cannot punch because it causes lot of stress. So, we drill a hole. Now, what will be the diameter of the hole? That is again specified by the standard, depending on the size of the diameter of the rivet at the shank, that is the shank diameter of the rivet, the hole size is selected. This is selected according to the standard. What we do then? We drill a hole. So, this is a hole, and then again we insert the rivet. This is the head part, and this is the tail part. We hold this by a fixture or a die together, that is this is the die or this is the fixture, and then we bring another die which has the similar shape. This die is brought in and then we apply pressure. Now, that could be done by hand or by some machine, some power driven system, and then it gets deformed. This tail part gets deformed, and when the complete deformation has taken place, we get the following shape. So, this is the permanent permanent joint made. Then we remove these two dies, that is these are now removed. This is known as die and this is to be removed. Then what we get? A joint which looks so, this is the riveted joint. Now, you see that it cannot be taken out without damaging this entire members. So, this part of the member part of the plate has to be damaged and then it could be disassembled. So, this is about the rivets. Now, you see that in order to make the rivets we have to give a large force. So, therefore, a compression will take place and with compressions there will be the stress developed. So, we have to relieve this stress. Now, there are two kinds of riveting. One is known as the cold riveting, where the mechanical force is given to the cold rivet, then a large residual stress developed and we will have to relieve this residual stress by heat treatment. So, cold riveting followed by heat treatment. There may be another process which is the hot riveting. That is, first this tail part is brought to a temperature which is a large temperature of let us say 1000 degrees Celsius, and then it is forged. Now, once the deformation takes place, then we have to cool it. So, there will be a tempering or quenching and tempering, then it has to be made with a specific standard, because otherwise we may get the different kinds of stress developed into the member. So, these are the different types of the riveting process. Now, the rivets could be used mainly for structural joints, that is the its purpose is to take up some load, right. So, it is also used to make a joint fluid leak proof, that is the joint has to be fluid tight, and then we have to do certain extra process, extra care. So, those are named as fullering or caulking. So, we have what is known as caulking or fullering to make the joint leak proof. Now, this you have to read from the book. There are various methods of caulking or fullering. So, you have to look at some reference book. What we can study now is what are the different types of rivets used. Now, for that we look up to some figure. Now, here these are the rivets for general purpose. Now, there are rivets for general purpose, that is to be used in the structural member. There are rivets for boilers, that is whenever we have a pressure vessels, we need the pressure vessels to be leak proof, and therefore, extra care has to be taken to make this joint fluid tight. So, there are different altogether different kinds of rivets available for the boilers. Now, let us look at rivets for general purpose. Now, if the diameter of the hole is less than 12 millimeter, then we use the following types of rivets. Again, these are made to some IA standard. There are standards available. You open up any book on machine design handbook, you will see those standards. Here you see, here the head is little bit hemispherical. So, this is known as the snap headed. We have this pan headed, which looks somewhat like a trapezium here, because this is in nothing but a conical frustum shaft. Here the diameter is d, and this diameter, that is the diameter of the head is minimum 1.6 times d. Normally the diameter is taken to be 1.5 to 2 times of d. Also, there will be cases where we get more than 2 times, that is here you see in the mushroom head rivets we have 2.25 times d. Now, it looks relatively flat, this face. We have counter sunk head 120 degree angle. So, this is again another type of rivet where the diameter is 2 d. Again, this is flat counter sunk head, which has including angle 90 degree. We have another type which has including angle 60 degree. Then this is round counter sunk. Instead of here a flat surface, we have a rounded surface, as you see here. Then we have a flat head, that is here the head is really a flat, and there is no counter sunk. Then if the diameter is more than 12 millimeter, but less than 48 millimeter, then we have these kinds of rivets. One is snap head. Here again it looks very much similar. The distance here is 1.6 d. We have pan head. Now, this is the length. We measure the length from this part. Here the height is 0.7. Again the height here is 0.7. So, this is pan head. Now, here the pan head with tapered neck. Here the neck is little taper, because it has a large diameter. So, there is a chance that there may be stress concentration here. So, we make the neck little tapered. We have a round counter sunk head 60 degree. This you are acquainted with now, because in last slide I showed this kind. Then flat counter sunk head with 60 degree angle, and then flat head. This looks almost the same as that which were shown earlier. Now, these are the rivets for general purpose. Now, when we go for rivets for the boilers, then we come across the following types. Here this is again snap head, but now it has a shoulder. Okay. Here you see the neck. Then we have ellipsoid head. Here the shape is ellipsoid. Now, these are made again by dies. So, by forging. Then we have a pan head, it looks very similar, but now here we have this kind of neck. Okay. Now, here invariably you will see that in boiler rivets you will have always this necks. Now, these are used for fullering or caulking, that is to make the joint fluid tight. Then we have again the pan head, but here the this angle is 60 degree. So, we have kind of pan head. Then again this kind, and we have this shape here. Here this very curious looking shape, but this is manufactured. Okay. So, these are the rivets used mainly in boiler. Now, we come to the point. So, we should know how many types of riveted joints are available. Now, the riveted joints are mainly of two types. One is lap joint and one is butt joint. Now, let us discuss one by one. Lap joints, suppose I want to join two plates, then one way of joining will be to bring two surfaces one above the other and then make a rivet. So, here is a rivet, so this is the rivet. Now, this kind of joint is known as lap joint. If you look from the top, then we have rivets here, number of rivets. These two are the parts of the two plates. Now, here these are the this row is the row of rivets. Now, here this is single riveted. Now, one important thing is this distance between two consecutive rivets in a column, that is, or in a row you can say. So, this distance is called the pitch of the rivet. Pitch. We can have also double rivet. Now, there are few possibilities. You see, there may be a rivet which is in that fashion. That is, there are two rows double rivet, and then these double rivets will be in chain riveting, that is, this everywhere there will be in a single row or in a single line there will be two rivets. Okay. If it is triple riveted, then there may be case where in a single line there are three rivets. So, this is the chain riveting. There may be situations where instead of chain riveting we have a zigzag or staggered riveting. How does it look like? It looks like the following. Here we have a rivet, here we have rivet, and so on. So, now there is a distance. Now, this is not on the same line, but it is a little distance away. Now, this length is known as PT, that is the transverse pitch. Now, it was earlier it was pitch, now it is transverse pitch, and this length, that is P, this length, diagonal length, this PD called the diametrical pitch. Now, you see that there is a relation existing between P, PD and P T, that is very easy to derive. Now, these are all about the lap joints. There may be a triple riveted, just like double riveted, there may be triple riveted, quadruple riveted, etc., etc. Bar joints, how does the bar joint look like now? Bar joints will be, here we have two plates which are kept face to face, there is no overlap between. So, these are the two faces of the plates to be joined. We bring one cover there. So, there should be one cover. So, this is a single cover bar joint. There may be double cover also. So, there are two covers, and through this cover and the plate we insert the rivet, that is there is a rivet through and through. Okay, this is the rivet. Now, this is known as the bar joint. Now, if you look from the top, there is the cover plate, and there are two plates which are to be joined together, and there are rivets throughout. So, this is again a single riveted bar joint. There may be two rivets, that is a double riveted bar joints is possible. So, there are two rivets, and this is again a double riveted chain type. So, this is chain riveting. We can also have a double riveted joint which is in zigzag pattern. It is just like the lap joint which I had drawn earlier. We can have triple riveted, again chain riveting or zigzag riveting. We can have quadruple riveted, which may be zigzag or chain riveting configurations. Now, these are the different types of riveted joints. What we now consider is the design of a riveted joint. Now, what you see is that suppose we consider a lap joint. Let us consider a lap joint with only one single riveted. Now, if you look at the plate, now it will be subjected to pressure. These two plates are subjected to pressures because it has to take some load. Now, we have this rivet over here. So on. The distance between two rivets is the pitch, and the diameter of the rivet let us say D. Now, you see without the rivet, the suppose instead of making it a joint, we had one single piece of the plate, then it's how much strength it could have taken. Suppose we have a plate of width, let us say P, we take this much plate, distance P, which this lies half between the rivet lies halfway between these two lines. So, therefore, if you take a plate of width P, then how much load can it withstand? The maximum load which could be withstood is P max is equal to the area. Suppose we take the cross section, that is the width T. So, P times T times the allowable, or that is the strength in tension. So, this is the maximum load which could be taken by this plate. We may have now with the rivet, its area of cross section is reduced. Now, here you see the entire area now gets reduced by this amount, there is a hole. So, therefore, with rivet, suppose now with rivet, the maximum load which could be taken is now P minus D, because this is the effective area available, the length is P minus D, something has been eaten away by this rivet, P minus D times T times S T. If you take more load, then what will happen? It will tear. So, this is the plate here, if you pull it, then it may tear somewhere here. So, it will tear. So, in order to prevent this tearing, we will have to restrict our maximum force to this limit. Now, sometimes we talk of the efficiency of the plate. Now, here what is the efficiency of the plate? The efficiency of the plate is the load, maximum load carried by the plate with rivet divided by the maximum load carried by the plate without rivet. Maximum load carried by the plate with rivet is P minus D times T S T, and without rivet it is P T S T. So, therefore, the efficiency is P minus D by P. Now, so you see the efficiency is very important, because the maximum load capacity has gone down by some amount. So, while designing a joint, we will have to design such a way that the entire load, that is the thickness or some other parameters has to be chosen, taking care of this efficiency or the fact that the joint has been weakened by introducing some foreign elements like rivets. We can have also other types of failure. What you see here is the failure of the plate. Now, the joint may also fail by shearing, that is what we see next. Now, here this is the configurations without any breaking. Now, it can fail, suppose there is a movement So, suppose the P is such that it moves this way. So, this part has moved. So, instead we have a rivet. Now, it was subjected to force. Now, when we make rivets, it is subjected to the normal force, right. So, there is a compressive force between the rivet head as well as the plate between two plates, and as well as here between the rivet plates and the head. So, therefore, a lot of friction force will be developed, and when we apply small p, so this p could be taken by this friction force itself, but if we increase the p, then the friction force gives away, and then because there is always some clearance between the rivet diameter and the hole diameter. So, therefore, one part of the plate will be in contact with the rivet and the other part of the plate will be loose. Similarly, for the lower plate, the opposite part will be in contact and the other part will be again loose. So, therefore, when we have this kind of situation, if P is large enough, then we have the force distribution something like this. Force distribution on the therefore, we see what will happen. Now, this part of this rivet is subjected to shear force. The shear force distribution looks somewhat like this, maximum shear force is P. So, therefore, if P is such that P by the area of this rivet, that is pi by 4 d square, if this exceeds tau max, then the failure will take place. Okay. Again, with the shear force there may be bending, but if the length is too small, then the bending could be neglected, but the bending may really occur. So, now we come to the case. So, this is the shear force distributions, the maximum shear stress is given here. So, therefore, the maximum P max due to shear must be equal to pi by 4 d square times S in shear, that is the strength in shear. Now, this is for the lap joint. Suppose we consider a butt joint instead of a lap joint, then what will happen? Then you see that for a butt joint, we have cover plates and there are rivets. Okay, there are again a single butt joint. Now, if you pull it by a force P and P, then if the P is large enough, then what happens? Then the bolt will be the rivet will be subjected to different kind of pressure distribution. Here this is the rivet, and this part is subjected to a large pressure P, and half will be taken by this cover plate and the half will be taken by this one. So, therefore, now we have the maximum, that is here the shear will take place, and we have the maximum shear stress to be now maximum shear stress is P by 2 here, because you can verify from this distribution that here if this is the total is P, then it will be taken P by 2. Therefore, in this section the shear force will be P by 2 and this will be taken by the area, and that must be less than T max. So, therefore, the maximum load that can be taken without shearing the rivet is now, so P max in shear will be equal to twice pi by 4 d square S S. So, now this is in double shear. Because you see from the last expressions we have multiplied by a factor 2, that comes because of the 2 cover plates. So, it has taken half the load with the cover plates. Now, this is how we can carry more load with the help of a butt joint, double cover plated butt joint. Now, with a single cover plated butt joint, of course, again the P max will be same as a lap joint, that is pi by 4 d square S S. Now, this is another type of failure of the rivet joint. Now, we come to other type of failure, that is when you look from the top on one joint, then what we see is that and here is a rivet. Now, what we see is that this rivet is subjected to other kinds of pressure also. So, here we have a distributed force, etc. Now, if this contact force is too high, then this part may be damaged. So, this is a crushing, right. So, we have the crushing failure, and although this is distributed, but the stress, the average stress developed will be equal to P divided by the area or the bearing area, which is equal to the projected area, which is d times the thickness, that is if the thickness is T, this will be the bearing stress, and that must be less than equal to sigma bearing. So, now we can take a maximum load to be P max in crushing will be equal to d T d times T times S crushing, which is the crushing strength. Now, this again the value of S crushing or the shear strength, etc., those are available from the table on the literature. They are available in the machine design handbook. You can have a look at them if you wish. Now, these are the different types of failure. Another interesting kind of failure may occur at the margin. How does it look like? Suppose we have a plate and the rivets are placed here. It is subjected to a force P. Now, if this length is known as the margin M, now it may happen that if this length is too low, that is M is too small, then the failure may take place here. So, entire thing may shear off. Okay. So, therefore, this kind of failure again can be prevented if we take M sufficiently large, and normal practice is that M is to be taken more than 1.5 times the D. Normally, it is taken to be 1.5 to 2 times D. So, if this safe distance is kept, then this failure could be avoided. Now, these are the types of failure for the single riveted joint. There is one thing called the joint efficiency, and this is defined that way, that is, we now define the joint efficiency. Joint efficiency is the maximum load that could be carried, and this is definitely the minimum of those loads, minimum of P in tension, P max in tension, that is the tearing, P max in shear and P max in compression. We will have to take the minimum of that divided by P max without any rivet, and that was P minus D times T times I am sorry, this is P times T P times T times S T. So, this is how joint efficiency is defined. Now, here you might have noted that we have defined the joint efficiency for one pitch length only. Now, when there is a running pattern, that is a row is formed for a large distance, then we can define the joint efficiency for a single pitch. If we consider the structural joints which has finite width, then we consider the joint efficiency for the entire joint, and in that case this P has to be replaced by W, that is the width of the joint. Definitely this is the total load taken by this joint, had it been one single plate and not the jointed plates. Okay. So, this is how efficiency of the joint is defined, but we have defined the failure patterns. We have discussed the failure patterns for a single chain, but if there are more number of chains, then various interesting and many other complicated things may happen. Take for example, a case where there are more number of so it may so happen that let me and so on. Let us say this kind of case. Okay. Then this is the pitch, this is the pitch, and there are more number of rivets in the second row than the first row. So, therefore, how many types of failure could occur? Suppose the P is large enough. suppose the force is applied here, there is a large pressure force applied and similarly force is applied there. So, a force is applied there. So, therefore, here it may tear from this point, this row. Okay. So, if the pressure of the force is such that if P is for example greater than P minus D, now again we consider the part of the joint which has width P. So, therefore, if you consider this part, then here the cross section area will be equal to P minus twice the radius of these bolts, because there or the rivets, because there are 2 rivets which participate, half of which participate every time. So, this is P minus D, this distance, and this times T, the thickness of the plate, times S T. If P is greater than that, then what happens? Then this part will be torn, but there are other possibilities also. Now, it may so happen that this part does not get torn, but something else, that is here suppose this row tears, this row tears, then what will happen? Then the tearing force necessary will be equal to, the tearing force necessary will be P minus 2 D times sigma times T times S T, and then once it gets torn, but it can be torn only by crushing or shearing of this. So, once this happens, then it is to be sheared. So, the shearing takes place, and therefore, the net force taken for shearing will be equal to pi by 4 d square times S S. So, this is the net force required to tear this part. Okay. So, we can define the efficiency, that is the force required for the joint to be broken divided by the force it can withstand. So, we will have to define the efficiency by using this formula, that is, this is the P maximum which could be taken. In a multiple, that is single or double or triple rivet, then there arise many such kinds of possibilities. Again, we have, when we have different rows, then the joints may fail by complete shear or complete crushing. How does it happen? Let us see. So, if the plate is quite tough, but the joint is not that hard, that is the weak joint, then what happens? All the rows or all the rivets could be sheared, and what will be the net force, that is the maximum force which could be withstood, that is P max, when everyone gets sheared, will be equal to the total number of rivets participating in a single pitch, that is 1, 2, half from this, that is 1 and 1. So, there are 4 rivets, complete rivets, therefore, 4 times pi by 4 d square and S S, or if the crushing strength is low, then instead of S S we will have to write S C, that is the crushing strength. I am sorry, then of course, this will be different, let us not then hurriedly make this statement. It is, if it is now covered by it is a butt joint. Now, it is a double cover. If this is a double cover, now this is for the single cover or maybe for the lap joint for a double cover. So, this is for the single cover. Now, if for the double cover we will have to multiply by 2 here, because every bolt will be the shearing of every bolt will be resisted by 2 cover plates. So, this factor has to be taken into account. Thus, given a joint, you have to know how to calculate the maximum force which could be withstood by this joint. This is how we can go for designing. Now, we come to the efficiency of riveted joints. Normally, the types of joints, now there may be lap joint, single rivet, double riveted, triple riveted. Normal efficiency, the range may go from 50% to 60%. For double riveted, it may go from 60% to 70%, the maximum which could be taken is 77. Here in the last case the maximum is 63. Again for the triple riveted we can have the maximum to be 86.6. So, you see if we increase the number of rows, that is if we go from double to triple, the maximum efficiency or the overall the normal efficiency goes on increasing. That is very natural, because if we make the joint more and more hard, then its load carrying capacity goes high. Similarly, we have when we have butt joint, then for a corresponding lap joint and butt joint, you see the butt joint has a larger capacity, that is the efficiency is large. It for the single riveted double cover, it may go from 55 to 60%, for double riveted 76 to 84, for triple riveted 80 to 88, and the maximum of 95% efficiency could be reached. For a quadruple, the maximum could be reached almost 99%. Okay. So, these are all about the efficiency of the riveted joint. Now, we come to the different standards related to riveted joint. So, we have the materials of rivets. Now, we know that general purpose rivets, they are made of steel or aluminum. Now, we have seen from the manufacture how the rivet is formed, that the material has to be hard, otherwise it will break, but at the same time material has to be somewhat ductile. So, the ductility is quite important. For the general purposes rivets are made from the steel, which has to conform this to the specifications given in these 2 codes. So, we must always refer to different codes, otherwise no design could be accepted in this national standard. The boiler rivets, which has to be enough strong, that is the fluid tightness has to be considered. Then we have to consider a different different standard. Then this is given IS 1990 1973, it was formulated in 1973. The strength and ductility of the rivet materials, as I said, it must be strong. So, the minimum of 40 megapascal is required, as well as the elongation has to be at least 29%. Again, the specification tells that it has to be heated to, let us say, 650 degree centigrade and again cooled, and it must retain this kind of properties, that is the elongation is 29% and sigma T, that is the strength, is tensile strength is 40 megapascal. The rivets and holes, rivet hole sizes which I talked of has a standard 1928 1961. So, these are the standards which are to be used. Now, we have known the various aspects of riveted joints. Now, you know how to calculate the strength of a riveted joint, how to calculate the efficiency of a joint, what kinds of rivets are to be used. Now, here is a homework problem for you, which of course, you have to the answer will be provided next class, but what it says that a double riveted lap joint with zigzag riveting, that is important. We need to have zigzag riveting designed for a 30 millimeter thick plate, assuming the safe working stress in tension, shear and compression are 80 megapascal, 60 megapascal and 120 megapascal respectively. Find the efficiency of the joint. So, here we need to joint 30 millimeter thick. Now, here I tell that the diameter of the rivet will be more or less this T in millimeter, when T is greater than, T is the thickness of the plate. Now, if it is greater than 8, then we can use this formula, which is called the Unwin's formula. Now, once we know this D, then we can refer to some handbook and get the efficiency of the joint. So, this will be provided, the solution will be provided next class. So, till then I take leave. Thank you. Dear student, let us begin the lectures on machine design part 1. This is lecture number 23 and the topic is design of welded joints. This will be the first part of the topic. Now, if you remember, welded joint is a part of the joints which is normally known as permanent fasteners. Let us look at the different other types of permanent fasteners. So, this is the slide which was shown previously in the last lecture. Now, I want to repeat that again. The permanent fasteners have two types. They are of two types. One is the components which are held by mechanical force and there are two kinds. One is the riveted joints, which we had discussed earlier, and the second one is the press fitted or interference fitted joints. The other type is that where the components are held by the molecular force. Now, these are the